Hey everyone, and welcome back to Forge College. I am super excited to be walking you through today's explainer. So, if you've been following along in our Solidity from Zero track, specifically the module on inheritance and interfaces, you know we've been deep in the trenches. In our previous lesson, Understanding Solidity Interfaces, we talked about how interfaces act like, well, conceptual blueprints. They tell us exactly what a contract should look like from the outside, but they don't actually do any of the hard work. Today we are taking those blueprints and physically building the machine. We're going to implement those interfaces into actual functioning contracts. So grab your hard hats because it is time to build. Here's our engineering schematic for the day. We'll be covering the blueprint meets reality, matching the function signature, overriding the interface, passing the compiler inspection, calling via interface type, and finally wrapping up your code.
All right, section 1, the blueprint meets reality.
Let's just dive right into this comparison. On the left side, sketched out in that crisp dark green ink, you're going to see iexample.sol. That's our interface. It declares a function called store and another one called retrieve. But notice how it just ends with a simple semicolon? There is no body, no logic, no state variables. It's literally just a flat, two-dimensional drawing on the beige paper. Now, shift your focus over to the right side, exampleimplementation.sol. This is where the magic actually happens. Look at those curly braces. We've got moving gears here. Inside the store function, we're actively taking a value and assigning it to a state variable. And inside retrieve, we're returning that stored value. That right side, that's the actual meat of the contract. The blueprint on the left tells the world what the machine can do, but the implementation on the right is what actually does it.
Moving on to section 2, matching the function signature.
Now, I want you to picture the Solidity compiler as this incredibly unyielding, almost comically strict patent inspector. I mean, this inspector will flat out reject your new machine if even a single microscopic gear is out of place. To pass the inspection, your implementation has to perfectly match the interface's function signature. First up, the function name. It has to be completely identical. Second, the parameter types and their exact order have to match. Like if the interface expects a uint256 and then an address, you absolutely cannot give it an address and then a uint256. It just won't fly. Third, the visibility has to match. If the interface says external, your implementation better be external. Fourth is state mutability. If the blueprint promises a view or pure function, do not try to alter the state in your implementation. And finally, the return types have to be an exact match. You see, a mismatch here isn't just some stylistic faux pas. It actually causes a fatal application binary interface, or ABI error, during compilation. The inspector won't just deduct a few points, they'll shut down your entire factory.
Okay, section 3, overriding the interface. So, simply following the blueprint isn't quite enough for our ridiculously strict compiler inspector. You actually have to officially stamp your paperwork to prove you're doing this intentionally, and that stamp is the override keyword. Whenever you implement a function from an interface, you must include this keyword right there in your function signature. Why? Well, it's a built-in safety mechanism. It's basically signaling to the compiler, hey, I know this function was declared in the interface I'm inheriting from, and I am intentionally providing the logic for it right here. If you forget that override stamp, the compiler might think you just accidentally created a function with the exact same name as the blueprint, which creates a really messy name collision. Sure, it feels like mandatory paperwork, but it keeps our code incredibly safe and predictable. Every single function you implement from the interface is going to need this stamp, no exceptions.
Which brings us to section 4, passing the compiler inspection.
Let's walk through this super practical diagnostic matrix for when the compiler inevitably starts throwing those bright orange errors at you. Take a look at the first row. If you see the error, function does not override any function, the likely cause is simply that you forgot your mandatory stamp. Or maybe your signature is just slightly off. The fix? Slap that override keyword on there and double-check your spelling. Easy enough. Now check out row 2. Type error. Overriding function changes state mutability. This happens when you have a mix-up with view or pure. If the interface promised a view function, but your implementation actually tries to modify a state variable behind the scenes, the compiler is going to catch you red-handed. The fix there is to make sure your implementation matches the exact state mutability promised in the blueprint. And then row 3. Incompatible return type. This basically means what you are handing back doesn't match the original specs. Just adjust your return types to align. Appeasing the inspector is honestly a breeze once you know exactly what they're looking for.
Up next is section 5, calling via interface type.
Let's map out the step-by-step workflow for actually interacting with our newly built machine. Step 1, like we just discussed, is compiling the implementation. Step 2 is catching and fixing those inevitable signature errors using that handy diagnostic chart we just looked at. Step 3 is making absolutely sure the override keyword is firmly stamped in place. But Step 4 is where it gets really exciting. Because once it's deployed, you don't just call the contract randomly. You literally cast the deployed contract's address to the interface type. This is how we safely reference the machine in our broader Web3 ecosystem. Let's see exactly what that looks like in the code. This brilliantly illustrates that casting process. Look closely at this little orange code snippet. iExample, example equals iExample, passing in impl. Here, impl is really just a standard Ethereum address. But by wrapping it in iExample, we're essentially telling Solidity, hey, treat the contract at the specific address exactly like the iExample blueprint. Then, right on the very next line, we can safely call return example.retrieve. Honestly, explaining this part always makes me smile because wrapping an address in the interface type like this gives us a wonderful ironclad compile time guarantee. The compiler verifies beforehand that retrieve is actually a balanced function and it knows exactly what to expect back. It prevents absolute runtime disasters and guarantees that the implementation behaves exactly as the blueprint promised. It really is an incredibly powerful feature of Solidity.
Finally, Section 6, wrapping up your code.
Let's just do a rapid-fire recap of today's key takeaways to really cement this in your mind before we wrap up. First, remember the absolute golden rule. Function signatures must match exactly. Name, parameters, visibility, mutability, and returns. No exceptions whatsoever. Second, the compiler strictly enforces this adherence. Our patent inspector is tough, sure, but fair, guaranteeing that all-important ABI compatibility. Third, you've got to use the override keyword on every single function you implement to signal your intentional design. And fourth, utilizing interface types in your code provides invaluable compile-time ABI validation, making your smart contracts incredibly robust and way more error-resistant. If you master these 4 points, you'll be well on your way to becoming a top-tier Solidity developer. But right before I let you go, I want to leave you with a bit of a provocative question. What if you only want to implement half of the blueprint? Like, what if you want to write some of the logic right now, but leave the rest for another contract to figure out later? We just established that interfaces demand 100% completion, so how do we handle a partial build? Well, that fascinating puzzle leads us directly into our next lesson module on exploring abstract contracts. You really won't want to miss it. This explainer was created by Forge College. To continue your Web3 journey, dive deeper into the subject, and uncover the answer to today's final question, make sure to visit our website at forge.college. Keep building, keep learning, and I will see you in the next lesson.